you already understood. Today we'll talk about the nanoparticle characterization and about our new device, which we released this year, on the beginning of this year. I will say a few words about the Cordouan technologies. So we are the French company which was based in 2007, and we are located in France, in Bordeaux. It's a city which is famous by making the red wine, and now I believe it will be famous by making the DLS instruments. We are not really big company. We have 12 highly skilled employees. And we developed the instruments for nanoparticle characterization. This is the portfolio of our DLS instruments from 2007. And we have already not small amount of the devices which are dedicated to characterize mainly spherical nanoparticles. So we have a Vasco which do the measurements in very opaque and concentrated solutions. Valleys, which make the measurements of zeta potential, Vascokin, which make the measurements in situ and without the contact with your suspensions and without the preparation even of your sample. And we have the 3-in-1 device Amerigo also for characterization of anisotropic particles. And today I will talk about the Thetis, which is depolarized DLS for characterization of anisotropic non-spherical particles. But before saying something about the Thetis, I will introduce the DLS, or dynamic light scattering. So DLS is the method which covers a big range of the nanoparticle size for the characterization. And the size of nanoparticle is important because depending on the size, we could have different properties of your material, of your particle. And this method is based by the tracking of the Brownian motion, which is the random motion of the particle within your solution. And thanks to the equation which was established in the beginning of 20th centuries, from tracking of the motion, we can calculate the diffusion coefficient of the particle. And using this diffusion coefficient, which is, this one, we can calculate the hydrodynamic diameter of the particle. And the method by itself is based, we send the light on the suspension with your particle, and we detect scattered light by the given angle. And thanks to the mathematical calculation and hardware correlator, we can calculate the size of the particle. So in the fact, you have the Brownian motion of the particle, you detect the intensity of scattered light. Using the equation, you are able to obtain the hydrodynamic diameter. So this is how look the intensity profile. Then you have autocorrelation function calculated, and by fitting this autocorrelation function, we are able to obtain the size. But how is possible to correctly fit this autocorrelation function to have the precise size? And in our devices, we're using 3 different algorithms to do it. So cumulants is the standard algorithm, which is mainly you can see in any scientific publication about the dynamic light scattering measurements, and it can give you the monomodal continuous distribution of the particle. So it's not able to determine if you have 2 different populations of the particle in the same suspension. In contrast, Laplace, it can detect different population, but it cannot give you the distribution of this population. So you have just a discrete value for your particle size. And the last mathematical algorithm, SBL, it can give you the continuous distribution of the different population of your particles inside your suspension. And using our software, which looks mainly like this, we are tracking the intensity of light. Then we are building the autocorrelation function, which is the blue data points. And using one of the 3 algorithms, you are able to fit this line, and you are able to see the residue of your fit. That means the difference between your experimental data and the fitting data. And thanks to the build it in all these mathematical equations, you are able to obtain the size of your particle and the distribution of the size, the polydispersity. But that was case of the spherical nanoparticles. And with time, we know that in our suspension, not really all particles are spheric. And for the past decade, the non-spherical nanoparticles become more and more used as in science and in the industry for production in new materials, new batteries, new medicines, and it has different shape, different aspect ratio. And knowing of the size and the aspect ratio of this particle are also important, as well as in case of spherical particles. This is the examples of using these anisotropic particles. So, as I said, it's for some advanced material, for optical material, for solar cells, for just to produce the material with combination of different properties. And mainly all these materials are made of anisotropic particles. And if we will look on the motion of this particle in the suspension, we are able to consider different ones. I will show you with the microphone, I think. So when you have a rod, it can move like that. That means the translational motion, but also it can rotate in your suspension. So it moves roughly like in all directions possible. And thanks to these two different motion, it's possible to detect two different dimensions of this particle. The equation on the slide describes mathematically these two different motions, which is linked to the translational and rotational diffusion coefficient. And you can see that in both of these equations, we have aspect ratio of the particle. So we can perform the calculation to determine the length and the width of this particle. And in our new device, the Thetis, we use the depolarized DLS principle. So in our device, we have the sample in the spherical cuvette in the center. I don't know, maybe this one will be more visible. No. In the center, and we send the polarized light on the cuvette, and then we detect the scattered light at given angle, and we can continuously change this angle from 30 degrees to 150 degrees. And on the detector, we have two different possibilities to detect. One of them is VV, when we have the same polarization of the light as the initial light, and the VH, where we have cross-polarized polarizators, so we detect depolarized light which were scattered by anisotropic nanoparticles. And thanks to it, because we know when we have the spherical, for example, and anisotropic nanoparticles in the same suspension, we will detect only the signal from the anisotropic nanoparticle on VH configuration, because thanks to this shape anisotropy, these particles are able to rotate the angle of polarized light, which was sent to the suspension. And it's, again, the equation which describes the autocorrelation function, which we are able to obtain on the two different detectors by collecting the scattered light. And we are able to build them and to feed them with the algorithm I described before. And if we will track this value of the autocorrelation function decay as a function of the angle of scattered light, we have the access to the information about the translational and rotational diffusion coefficient, and that's mean to the length, width, and aspect ratio of the particle. Obviously, you don't need to know all this equation to do the measurements, because it's in our software, and you just need to do your measurements and to obtain the results. So the Thetis, the multi-angle DLS, and SLS device, what mean dynamic light scattering, depolarized dynamic light scattering, and static light scattering, is the device which is able to detect the size of spherical nanoparticles, of anisotropic nanoparticles, and the bar diameter of the nanoparticle or molecular weight of your polymer, for example, without preparing the calibration solution, since it has access to the different angles. Also, in this device, you have real-time time-resolved dynamic light scattering, so you are able to track the kinetic of your particle growth, for example, the changing of the particle shape with time. And as well as in our previous devices, for fitting the correlogram, we have access to the 3 different algorithms of mathematical algorithms to fit the experimental data. And this device is operated by ProTheta software. So in this ProTheta software, you have 3 different options of measurements: SLS for the molecular weight of your polymer or bar diameter of your particle, DLS for spherical nanoparticle measurements, and DDLS for anisotropic nanoparticle measurements. I won't describe you the spherical one, so I will switch directly to the anisotropic nanoparticles. And you can see that, in fact, by tracking the scattered light on 2 different configuration of the detectors, we are able to obtain 2 different autocorrelation function. And by fitting this autocorrelation function, we have the different size distribution of your particle. And by plotting this autocorrelation function as a function of angle, we are able to build in software this beautiful linear dependence of the autocorrelation function decay, and to determine the lengths and the widths of the nanoparticle, what we did for the gold nanoparticle rods. And we compare these results with the TM observation made in our laboratory, and as you can see, it's quite similar to the one which we obtained with our device. So it's really can give you information about your nanoparticle. For sure, it's not the same because the statistic of the dynamic light scattering is much higher, and the difference between electron microscopy and dynamic light scattering method is that for electron microscopy, you see the bar diameter of your particle. In contrast, for dynamic light scattering, you see hydrodynamic diameter of the particle or length, because it's surrounded by the cloud of counter ions, and it moves together with this counter ion. So it also takes into account of the size. So we repeat these measurements for different type of rods, and we obtained nearly the same values for TM and for depolarized dynamic light scattering, and we proved that this device is able to measure the lengths and the widths of your nanoparticle within I don't know, tenths of the minutes, depending on the amount of angles you want to measure. And it's first device which exists for now in the market, which is benchtop depolarized DLS, so you probably won't be able for now to find something similar. It's quite unique. And on this, I would like to thank you for your attention. And if you have some questions, I'm in the booth of Pragolab, which is on right or on left from the entrance.
Exactly, exactly.
Yeah.
So Hanna will be available for any kind of technical or application questions.
Or if you need translation on Czech, my colleague will translate you.
Yeah, exactly.